So we're continuing on with looking at computing the forces on a submerged curved surface. And in the last segment what we did is we found the forces that are acting on the curved surface. We're making an approximation, so we're finding resultant forces. Now what we want to do is we want to find out where those forces are acting. If you recall, for planar surfaces, that was the center of pressure. So essentially we're looking for the center of pressure for this curved surface. And what I'm going to do, I'm going to redraw our fluid chunk, which is above the curved surface, and we're going to rearrange and define some things that will enable us to then determine the location of where these forces are acting. Okay, so here we have a schematic of our surface that we're interested in. Remember, this is the surface here. In the last segment, we came up with an expression for Fry and Frx. However, we were not able to, or we have not yet done, is determine where these forces are acting. And so those are the unknowns that we have. The way that we're going to do this will be very similar to what we did for the planar flat plate. And if you recall there, we sum moments about some location, and for here what we're going to be doing is summing moments about the origin that we'll call O. I've introduced a coordinate system with respect to that origin, and that is the X and the Y that we have on this plot. So what we're going to do, we're going to look at all the forces that we have acting. We have FL, we have FT, we have weight, and then we have Fry and Frx. Those are the forces. We'll sum moments and then try to figure out where the location is for those two forces, the Frx and the Fry. Okay, so that's the equation that we get for the summing of the moments. Now there are a couple of things we can say about this expression. First of all of these terms here are known. And the other thing that we know, we from the last segment determined the forces, so those are known as well. So the unknowns, we have two unknowns, this, and we only have one equation. And what we're going to do, we're going to make a bit of a general rule assumption for the vertical surface and the FL and the Frx force. So let's take a look at that now. Okay, so we have this as being a general rule. So what is that saying? Well, if we look at our curved surface, recall we had this force here, but we also have a projection of that area on this surface here. And so that was the force in the x direction, Frx. And we also had a force this way, which was FL. Well, it turns out those two are essentially the same, equal and opposite, and they're acting at the same location. So this here we said was YL, Y1 was here. It turns out Y1 is equal to YL, and they're equal and opposite to one another. So that's something that we will use to be able to simplify the equation that we have for summing of the moments. So let's take a look at that. So we get FL is equal to Frx and Y1 is equal to YL. And if you recall, YL is the center of pressure of the vertical surface AC. So with that, we can look back to our analysis for planar surfaces, and that tells us that Frx acts at it will be the center of area of the surface AC. And we need to find the center of pressure here, so we have this term. So we get that expression, Now what we can do, we can go in and determine IXX, theta, and AAC. AAC, if you recall, is this surface here. We have A to C. So what we're talking about is this surface right here. So let's look at the values. We have theta. Theta for that is equal to 90 degrees. IXX BL cubed divided by 12 using the dimensions that we have from our schematic. We have L being that dimension. We said it's width B into the screen. And finally, the area of AC is just B, the depth or width into the screen, times L, which was the height. So we have those. We can plug them into the equation. And with that, we get Y1 we get Y1 is that. It's just the center of area of AC modified. And if you recall earlier, so if this is the center of area here, the center of pressure is going to be a little bit below. And that determines Y1. Now what we will do, we'll go back to our moment equation, summing of the moments. So this equation here, and we're going to plug in what we now know in order to try to isolate. And in this case, we're going to be trying to isolate x1. So let's work that through. So we get the equation for x1, and we plug in the values. And finally, we can solve for x1 as being the following. So that gives us the equation for the x component of the resultant force on our fluid element. So what we had a plane or a curved surface under the water. We said that that was A. We put that as being B, and we put that as being C. Let me double check to make sure that was right. No, I goofed that up. I apologize about that. So we had those flipped around. That was A, that is B, and that is C. Double check to make sure. B was on the right. Yeah, okay, so we have that. And what we did is we solved for these forces here, which we had Frx and Fry. But what we were doing now is trying to figure out where they act, and what we did is we defined y1 as being this direction, and then x1 as being in this direction, both from this origin. So the force acting, it could be something like that, and then it would be like that on the surface. And that would then give us, so the center of pressure is not exactly right on the surface as we get from this analysis, but it's an equivalent force, and consequently it gives us an indication as to where the center of pressure would act if you went through and you did the full, complete, complex integration that we looked at the beginning of this segment. So that is forces on a curved surface. Obviously, a planar surface is a little easier, but curved surfaces are a little bit more complex, and this is a technique to enable you to figure out what that force would be and where it would act.